So this is, so I'm going to talk about combinatorial Walrasian equilibrium. It's a joint work with Brendan Lucier and Nick Gravin. And does anybody recognize this date?
It's a date?
October 29th, 2012. What happened then? No? That's Sandy. Oh. So this talk was supposed to be given on October 29th, 2012. And thanks to Edna, who prevented my arrival that day, which I'm very thankful to. This date has changed now, and now it's April 30. So I'm happy to be here. So let me describe you at first very generally what's the kind of setting I'm looking at in this work. So let's suppose we have a seller, and this seller has some set of goods. Let's say here some set of fruits. And on the other side of the market, there are just buyers. And these buyers come to the market with some preferences in mind. And these preferences are usually given by what we call valuation functions. And these valuation functions, generally what they do, they specify what is the value. So let's say we take this buyer here. This buyer here has some value that she assigns to every subset of these items. For example, Alice here, she's just hungry, so she wants a single fruit. So her valuation is $3 per fruit. And it doesn't matter what fruit she gets. She's just hungry. She wants to eat. And usually, we specify the value of some buyer to some item by a monetary amount. Okay? How much dollars does this worth to him or to her?
So you did specify for all subsets, just for single.
Right. So she's just what we call a unit demand buyer. She wants one fruit, and her value for every single fruit or for every superset of any fruit is $3. This is just an example. In general, we can imagine that these valuation functions can exhibit different types of substitutes, complements. For example, this buyer here, she actually wants to prepare a fruit salad, so she gains no value from a single fruit or a pair of fruits. She only wants all three fruits, and if she gets all three fruits, she can make her a fruit salad, and then she has value $7. And more generally, we can think of this exponential size object, VI, which is the value of agent I, which specifies the value for each subset of items. And we'll get to the model soon. Then we have an outcome, and the outcome specifies exactly for each buyer what bundle he receives in this outcome, and possibly also what payments he needs to pay. So for example, this is a possible outcome. The orange goes to Alice, and she pays $3. And the strawberry and bananas go to Bob, and he pays $10.
So you have one of each item. Or
We
if
ha-
you have multiple,
we have one of each item, and the one banana item is actually 3 bananas.
But if you have more than one, I mean, if one can get more, you explicitly have it in the goods. So separate.
Exactly, a separate. So when I say a good, it's one good, and that's what I have. And it's very important that in my work here, I assume that the goods are indivisible. Okay, these are.
So this is the difference between combinatorial markets and markets as in macroeconomic theory.
Right, so in macroeconomic theory, the focus is on markets with divisible goods. They assume like convex markets, everything is divisible. Then they have Fisher market models, and also the Walrasian model is different because everything is divisible, so things are easier. And they have very general equilibrium theory. And now we move to indivisible goods, and things change, and we need to handle it. Was Klim, did you have a question? Oh, okay. Okay, great. So let me tell you how this talk is going to proceed. In the beginning, so now that you understand the spirit of the model, I'll go to define the model formally, what I mean by a combinatorial market. Then I'll describe to you a very appealing solution concept, which is called a Walrasian equilibrium, which is something that I'm sure you will all agree that it's a beautiful notion. And the only problem with this notion is that it very rarely exists. It exists only for very specific subset of valuation functions of the bidders. So we would like to come up with some way to generalize the beautiful theory of a Walrasian equilibrium to general markets with general valuation functions. And for this, we will introduce the concept of bundling. We will allow, in some very restricted way, we will allow the seller to do some bundling over the original set of items. And then we will completely solve the existence problem, and the challenge will become to recover good outcomes. Okay, so we'll have existence always, and the question will be, are there good outcomes? And our main result will be that we can always get half of the optimal social welfare, and here I mean the unconstrained optimal social welfare in an equilibrium, in the equilibrium notion that we will define that uses bundling. Okay, and then we'll discuss also some additional results, but these will be the main result. So let's start with the model. So as I said before, in the model here we have a single seller, and he has M indivisible goods for sale. Yes?
Just want to clarify one thing. When you say that the half of the welfare can be achieved, you mean the existence of this thing, or you mean you actually compute this?
Okay, great question, and I'll get to it. So it will have a computational aspect, but not all the way. And when we get to it, ask this question again, and I'll describe exactly what I mean by this. Okay, but I'll definitely discuss both the existential aspect and the computational aspect of this result. Okay, great. So we have M items for sale. These are indivisible items. We have N buyers. And every buyer has a valuation function, VI, that takes some subset of the items and assigns to it a real value. We make some very moderate assumptions that just normalization assumption, the value for the empty set is always 0, and monotonicity assumption, if we have a set S which is contained in T, then its value is at most the value of T. And for those of you who are familiar with literature on what's called algorithmic game theory, usually the assumption in auctions is that values are private information of the buyers. And this is like the main challenge then is to design what's called a truthful auction, which is an auction where every buyer has a dominant strategy to truthfully reveal his valuation. Here, we actually assume full information setting. Okay, so suppose the seller knows the valuation is well known, it's common knowledge. The challenge comes from a different place in our work. Okay, because we will require some very strong equilibrium notion, and that will be the challenge.
So are you going to explain how this is given? It's an oracle or it's a circuit? How is the...
I'll explain. Yeah. So it will be so the access to it will be given by what's called the demand oracle, and I'll define it then when we get to it. Great. What is an allocation? An allocation is just a partition of the goods. What goes to who? So Xi is the subset of items given to agent I. And the social welfare of an allocation is just the sum of the valuations of the different buyers. And this is a very important objective function, and this will be the objective function that interests me in this work. Okay, I would like to maximize social welfare. Great, and I mean this is a very it's usually in economic, like this is one of the main economic goals that is usually studied in the literature. I mean, some works want to maximize social welfare, some works want to maximize revenue. In this talk, I'll actually talk mainly about social welfare. We have some results on revenue, which maybe I'll mention in the end. Okay, so let's, so as I said, now we are going to discuss what we want is a very simple pricing mechanism. We don't want any fancy auction, truthful auctions. We want very simple pricing mechanism, and let me describe to you what I mean by simple. So what I would like from the sellers is to just set item prices for each good. So P is a price vector, and for every good J, it specifies just a price of this good. And now the buyers come to the market, and they are faced with this price vector, okay? A price for each item, and they have their valuation function in mind. So then I will define the utility of an agent I who comes to the market and gets a bundle Xi. This is Ui of Xi, the utility of agent I, given that he gets allocation Xi under these prices P. as the difference between his value for the goods that he gets and the sum of prices. Okay, so these are just PJ, just item prices. He's getting so much value. He needs to pay that much, so that's his utility. And we say for a specific set that it is the demand of a specific buyer if it's a bundle that maximizes this utility. Okay, so we can imagine a buyer who comes to the market. He has his valuation function in mind, which specifies what is the value for each bundle. There is a set of prices, and then he comes and says, what's the bundle that maximizes this formula? Okay, and this is his demand. There can be many such bundles. Okay, so, and each one of these will be called a demand set for this buyer.
If there are two identical goods, do you require the prices are the same for them? Identical goods, I mean.
So you know, in my model, I just have M goods, so there is no such thing as identical.
You can still define you have two goods, such that each buyer has the same value for both goods.
Oh, okay. Oh, in this, so in terms of the valuation, I do not require any additional restrictions on this price. Okay. In the equilibrium, this will need to be the case because of the equilibrium notion that I'll describe, but up front, I do not require anything.
You're going to want the demand sets to be distant, like non-overlapping or something for different.
Definitely. So let me.
Force it
Exactly. So let me get to the solution concept, and all of these questions will be summarized in this solution concept. So let me first describe to you what a Walrasian equilibrium means. And like, okay, so just like all the comments that I heard from you now, we can like go through a thought experiments, and we can think what's a dream solution that we would like in such a setting, right? We would like something simple. So we don't want fancy bundle prices. You know, we don't want that. You know, for every bundle there will be a different price. We want to keep it simple. Okay, item prices. Also, we want the solution to be fair. So, for example, we don't want we want the prices to be anonymous. We don't want, you know, that if Jean comes to the market, I tell her, okay, orange for you is $1, and if Avi comes to the market, I'll tell orange for you is $3. We want to keep it. So I don't want that. I do not discriminate. And moreover, it will be a much stronger notion of fairness. In this, in the end, in this equilibrium, no agent will ever envy any other agent. Okay, so no one will go back home and say, "Wow, I wish I were Avi." Okay, I wish I got Avi's bundle, and I would be willing to pay what Avi paid if I would just get Avi's bundle. So it will be fair, and also it will be stable. So let me now formalize what I mean by this. So a Walrasian equilibrium is a tuple of allocation and prices, which satisfy the following requirements. First of all, xi is a demand set for agent I given p, and there is no, just like your question, there is no overlap between the demand sets of the different agents. And in addition, all items are sold. This is a property we often call market clearance. So we see that, I mean, this requirement here says that there is no overdemand, there is no overlap. Every agent comes to the market, looks at the prices, gets exactly the bundle that he wants, and there is no overlap. The market clears beautifully. And also, all items are sold. Really, what I mean by all items are sold, that if there are items that are not sold, their prices is zero. Okay? So this means that we have no over-demand in the market and no oversupply. The market beautifully clears, and every agent goes home with the bundle that he really, I mean, the one that maximizes his utility.
So this is like an error de Boer, but integral.
Exactly. Exactly. And error de Boer have very general existence theorems, but we don't have it here with indivisible items. So we are definitely not the first to study this solution concept under indivisible items, and there are a lot of results about it. First of all, if a Walrasian equilibrium exists, then it always maximizes social welfare. And it doesn't only maximize social welfare among all integral solutions, it also maximizes social welfare among all fractional solutions. And later, I'll get to the linear program, and I'll go over this proof, the proof of this efficiency, and I'll show that, in fact, we have a very beautiful characterization of when can some allocation be supported in a Walrasian equilibrium, okay? For some allocation, we said that it can be supported in a Walrasian equilibrium if there is a price vector that together with this price vector, it makes a Walrasian equilibrium, yes?
It seems that this property is stronger than what you get in the error of the Bohr model, because there you are only guaranteed some kind of Pareto efficiency. It doesn't guarantee to maximize.
Yeah, it's true. It's in the same spirit of error de Boer, but not quite. As you say, there are differences.
But it seems even much stronger.
Yes, definitely. Okay, so now we come to the hard part. So, I mean, everything until now was beautiful. It's a beautiful notion. It's simple. It's fair. It's transparent. Many advantages. If it exists, it's always efficient, but the problem is existence. So it is known that if the valuation satisfies some notion of substitutability, items are substitute to each other, the specific property is called gross substitutes. I don't want to get into the exact definition, but what you should have in mind is that, you know, items are not complements to each other. They are substitute to each other. Then, if all valuations satisfy this requirement, then a Walrasian equilibrium always exists in this model. And in addition, in some sense, I mean, this is good news. The bad news is that in some sense, this gross substitute property is, in a sense, a maximal set of valuations for which we have this general existence theory. And moreover, if valuations satisfies gross substitute, then we have a very natural process, which we call a atonement process, that will lead us to this equilibrium. And this will be a very natural process where we just start all the prices at zero. All the agents come to the market. They say what is the bundle that they want the most. And if there is an item which is over-demanded, its price increases until one drops. Prices increase naturally until the market clears. And if valuations are substitutes, gross substitutes, this simple process will result in a Walrasian equilibrium.
It's a greedy algorithm.
Greedy.
What is the origin of this word atonement?
It's a great question, and I don't know. I don't even know how to pronounce it.
Yeah, what is this? That's like Walrasian. I never
Whenever I try to say it, people will correct me.
What's the word?
I've seen the original version. I know it's about unit demand options.
No, what's the meaning of atonement?
So I looked it up because I was curious, just like you. And in Google, what I could find is that they define it as some investigation process. And it's always, you know, I couldn't find the definition of this. So I couldn't find the definition of this word in a dictionary. I could only find it in Google in the context of this equilibrium notion.
Isn't this the Hungarian algorithm, the unit demand options?
Mm-hmm.
That, I mean, the Hungarian algorithm works exactly like this. It defines stable matching.
Yes.
Defines unit demand options.
Yes, it's very closely related to matching algorithms.
Are
But
there any connections to like matrix theory here? I mean, it almost looks like some
because it's greedy, right? So
well, I mean, also, you know, the way that I guess you're going to have some linear program characterizing, you know, the set of fractional solutions.
Right.
The Walrasian be optimal with respect to it. It looks like, you know, one of the relaxations for, you know, one of these like matrix polytopes types of things.
yeah, maybe.
So it doesn't work for submodular.
It doesn't work for submodular. It doesn't work for submodular, and it doesn't work for much smaller sets. I mean, smaller classes of valuations. Gross substitute is very, very restricted compared to submodular. So informally, what it means is that, say you have a vector of prices, and under this vector of prices, you have some demand. You demand some subset. What it means is that if you increase some of the prices, you will never stop to demand the items whose prices did not increase. Okay? And in this sense, items are not complement to each other. So if you can think about, you know, right shoe, left shoe, I mean, you demand right shoe and left shoe together. If you increase the price of a left shoe, you may not demand the right shoe anymore. Yep. And this cannot happen if the items are gross substitutes. Okay, so this is what happens when items are gross substitute, and as I said, gross substitute is a very, very restricted subset of valuations, much more restricted than submodular. I mean, I can think of different valuation classes in between those two, which we still don't know to say much about.
So
but
there are general submodular functions which the Walrasian equilibrium doesn't exist?
there are, what's the question again?
There are like submodular valuation functions for which the Walrasian equilibrium
Definitely, and I'll show you one. I'll show you one very specific one. Oh, let me just tell you that if the submodular valuations that are symmetric are gross substitutes. Okay, it's only asymmetric submodular functions that are beyond gross substitutes. Okay, so here's the dark side of Walrasian equilibrium is that the gross substitute condition is very restrictive, and for more general Bayer valuation, it does not exist. And as I said before, gross substitute in a sense is the maximal subset for which Walrasian equilibrium exists, and it's in the following sense. For every valuation function that is not gross substitutes, you can add what we call unit demand buyers. Unit demand buyers are buyers that are just interested in a single unit in the market, such that the market will not have a Walrasian equilibrium. Okay, so we think of, we want every class that we talk about to include these simple unit demand buyers. So in a sense, it's a maximal set for which it exists. So let's look at, let's start to get a feeling of what's the problem here. Why can't we have a Walrasian equilibrium? And this might lead us to the solution that we want. So here is a very simple scenario. We have two buyers, buyer 1 and buyer 2. And we have two items, left shoe, right shoe. And this table specifies the valuation function of the two buyers to every subset, to left shoe, right shoe, and to the bundle, left and right, okay? So the first buyer, he actually wants just a single shoe. I don't know why, but he wants to throw it on someone. So he's happy with one shoe, and getting the second shoe doesn't give him any additional value. So he gets value 3 no matter what he gets. The second agent is more reasonable. He wants the pair of shoes, and he gains value 4 from getting the shoe. Now let's think about a Walrasian equilibrium in this scenario. So we already know that if a Walrasian equilibrium exists, then it maximizes social welfare. So it must be that in the Walrasian equilibrium, the allocation should be to give the pair to this agent 2 here, right? Now let's think if we can come up with a price vector that supports this allocation. We know that the price, the item prices cannot sum to more than 4, because otherwise this agent will not want this bundle. But then there must exist at least one shoe whose price is at most 2, but then agent 1 will want it, right? So we cannot support this allocation, the optimal allocation in this scenario, so therefore we do not have a Walrasian equilibrium. So the motivating question for this work is whether we can extend the beautiful theory of Walrasian equilibrium beyond gross substitute valuations. Ideally, what we would like is for general valuation function. We don't want to restrict it at all. Submodular would not be enough for us. Subadditive would not be enough for us. Nothing. We want general valuation function. We want somehow to take this theory and to extend it beyond gross substitutes. So let's go back to this definition of a Walrasian equilibrium. What we demanded is that so in a sense, this is a two-sided equilibrium notion. We want that the buyers are maximally happy with their allocation, and we want that the seller is also in equilibrium in the sense that if there are items that are unsold, their prices is 0. Okay, this is some notion of stability from the seller's side. But if we are now playing the role of the seller in this market, then we can actually say, well, if our objective is to just maximize social welfare, just relax this requirement. Okay, let's stick to, we still want all the buyers to be maximally happy. This will be our equilibrium notion. But we will allow unsold items in the market. This is fine. As long as the seller can commit to not selling these items, we are fine. If our objective is to maximize social welfare, if there are some items that are not sold, fine.
How it can help.
Okay, let's see. Okay, let's see if it can help.
So then you don't require a good price is 0 if it is unsold.
Exactly. We allow for some unsold items to have price greater than 0. This is exactly the relaxation that we are doing here. Okay? And then, so we define stable pricing or stable solution now will be exactly one that satisfies this condition here, but not necessarily the second condition. Suddenly, of course, we have existence for general valuation functions, because specifically we can just assign, a price of the maximum value of any agent in the market, and then no one will want anything, and everybody is maximally happy. So the question is, can we support a good social welfare? Okay, social welfare, I remind you, it's the sum of the agent's valuations from their allocation. So we have existence for free, and the question is whether we can achieve a good social welfare with relaxing this. Unfortunately, this will not be enough. So just relaxing the seller's side of the market would not be enough in the following strong sense. There exist valuations such that for every stable outcome X, the social welfare of it will be at most a fraction 1 over m, number of goods, of the optimal social welfare in the market. Let me give you an example. Let's say we have m items, so this is the m items we have, and we have 2 buyers. One buyer, again, he's a unit demand buyer. He wants any single item for a value 1 plus epsilon. Okay? No matter what he gets value 1 plus epsilon as long as he's... And the second one wants it all for a value of m. So what will happen here? Obviously, the optimal thing would be to give everything to the second buyer for a value of m, but then there is at least one item whose price is less than 1, so agent 1 will want it, so we cannot support it.
Just a generalization of the shoes to M.
Exactly. Generalization of the shoes to m, and then it means that we cannot get better approximation than m, which is linear in the number of items, which is very bad. So it means that just relaxing the second requirement is not sufficient in order to get something meaningful.
So again, the optimal is just the sum of all partitions of the valuations of the players on the parts.
Yeah, the optimal, so we have social welfare. So we have x, which is the allocation, which is a vector of allocation, x1 to xn. And social welfare of x is just the sum of I of vi xi. And this is what we want to maximize. Okay, so the opt is just the x that maximizes this thing here.
In general, computing this number is hard, right?
Yes. In general, and also even for specific valuation function, like even for just super additive valuations, you cannot get better than square root m. I mean, depending on depending on the query model of the Oracle model. Yes?
That's what I was going to ask.
Okay, yeah. Okay, so in general, it's hard, and we'll get to it. And let me also mention that, I mean, here so here we had unit demand, and we had buyer 2 has very strong complementary aspect to his valuation. But even for sub-additive valuation, and in fact, even for what's called fractional sub-additive valuation, which is a subset of sub-additive valuation, we can still get a linear gap under this equilibrium notion. Okay, so this is very bad, and this will not be sufficient. So relaxing market clearance, I mean, the second requirement is not going to be sufficient for what we want. So we can relax the first. And in fact, there are some notions of equilibrium in the literature that try to relax the first. And when they relax the first, what they say is that we want agents to be happy, and we want agents to be maximally happy, just like here. But we want them to be maximally happy, not with respect to all possible things they can get from the market. For example, we do not want them to want to add any specific item to their bundle, but we are fine if they are willing, if they would prefer to drop some items from. We would allow that, okay? And we don't want that. We really want that, given the pricing structure, agents are absolutely maximally happy with what they get. So what we will relax is the pricing structure. And let me tell you.
Reciprocity. We're just going to allow items to be bundled.
Yeah, that's what we will allow. But it will be very different from previous work that allowed bundle pricing, because after we bundle the items, we still require it to be very simple. And now I'll describe exactly what I mean by this. So let's revisit our example. This is the shoe example. We had no Walrasian equilibrium. And this is a possible solution for the seller. I mean, I heard that some sellers already thought about this solution. why not commit upfront to the pair, right and left shoe? Just sell them together, sell a pair. And then we can sell the bundle of left and right to the second. We can set the price of 4 to this bundle, and we are fine. We have an equilibrium, right? And we are all done. So this leads us, this simple observation leads us to our proposed solution, okay? And the proposed solution is exactly that of bundling. So this is exactly what I mean. What I would allow the seller to do is to redefine the items for sale. In what sense? I would allow him to pre-package items into bundles. So just impose a partition over the items, and then this will define the new market. I no longer have right shoe and left shoe in the market. I have a new item that is called a pair of shoes. And so these defined bundles induce a reduced market. And now I would like to find equilibrium prices for the items in the reduced market. Now, when I say equilibrium prices, I make the exact same requirements as before. Everything should be linear. I do not allow different prices for different, bundles. So all I do is before the market resumes, I would allow the seller to redefine the items for sale by imposing a partition over the items for sale. And now I want a Walrasian equilibrium, or just, in this work, just the first requirement. I want every agent to be absolutely maximally happy. But I would not allow the buyers anymore to buy subsets of the original bundles because there are no such items anymore in the market. The items are redefined.
And the bundles are disjoint.
The bundles are disjoint. It's just a partition. Yeah, integral partition. Why do I have to? Okay, great question. And let me start the first half of the talk. I'll just talk about what happens when we relax the second thing. Your question, I guess what you have in mind is that if you allow bundling, you don't have existence problem anymore, even if you do not relax the second requirement, because specifically you can, in particular, what you can do is just bundle everything together. You have gross substitutes and you have existence, right? And the question is, can you approximate well the optimal social welfare? We don't know yet. We do not have an answer for this question. We do have an answer if we do relax the second requirement, okay? So this will be the focus of this talk. And then in the end, we'll also mention exactly, we'll address your question. Okay, any other questions about this? Because, this is what I want you to understand. This is the most important slide. This is the new solution. We want bundles, and then once we have bundles, we want the Walrasian equilibrium. And this is exactly the idea behind what we define as the combinatorial Walrasian equilibrium. Okay, and so let's define it now formally. So we have some allocation. This is x0 is the unallocated items. x2 is the items that are allocated to agent 2. x4 is the items allocated to agent 4. And we say that allocation x induces a reduced set of items. So we no longer have A3, A4. We have the bundle x2. This is the new item. And they are defined as the bundles of the allocation, where x0 is the set of unallocated items. And now we will say that the tuple x, allocation x with prices p, and now the prices will actually be the prices of these bundles, okay? For every bundle, we will have a price. So we say that this tuple xp is a combinatorial Walrasian equilibrium if xp is stable over the reduced set of items induced by x, okay? And we have an allocation. It induces a new market with those bundles, and we require that every agent is maximally happy with his allocation, and then we say that this is stable, that this is combinatorial Walrasian equilibrium.
So hypothetically, if we took the optimal, social welfare solution, right? So that induces a partition on the
Yes.
items anyways. What's wrong with just putting the price for each particular bundle at whatever person values it?
That's a great solution if the valuations are super additive. And in fact, if the valuations are super additive, this is exactly what we do, and this will be a combinatorial Walrasian equilibrium. But as we will see very shortly, if valuations are not super additive, this will not be a sufficient condition. We may have a problem. Great. So obviously, a combinatorial Walrasian equilibrium always exists. And as Klim said, even if market clearance is not relaxed. And the new question is, how well can a CWE, or combinatorial Walrasian equilibrium, approximate the optimal social welfare? This is the main question that we would like to study. Okay, this takes us, our results relate very strongly to the relation to the characterization of Walrasian equilibrium existence, which goes through the linear program of the problem. So this is called the configuration LP of the winner determination problem in a combinatorial auction. Let's look at this linear program. So what we want to do, we have these variables YIS for every agent I and bundle S. And what we want to maximize is exactly the social welfare, which is the sum of IS of YIS VIS. Okay? Let's think for now about the linear program relaxation, where YIS is between 0 and 1. It's fractional. Okay? So this is exactly maximize the fractional, the social welfare when we allow fractional solutions. What are the restrictions that we have? We require, of course, that every buyer is allocated at most one bundle. So we want for every agent I, the sum of S of YIS is at most 1. And for every item J, we allow each item J to be allocated to at most one buyer. So for every J, we want the sum over I and S that contains J to be, of YIS to be at most 1. And we want this YIS to be between 0 and 1 for every I and S. Okay, so this is the linear program relaxation. Of course, if we require that YIS is either 0 or 1, this is exactly the problem. This is the integral problem that we are interested in. This is the linear program. And this is a very nice theorem that characterizes exactly what allocations can be supported in a Walrasian equilibrium. And what it says is that an allocation X is a Walrasian equilibrium, or in other words, there are prices such that together they support a Walrasian equilibrium, if and only if, essentially what this says, if and only if there is no integrality gap in this problem. Specifically, if and only if the optimal fractional solution to the LP occurs at the integral solution that sets exactly yi of xi equals 1. Okay, so it says, so basically what it says, if this program has no integrality gap, then we take the optimal integral solution to the problem, and this is a Walrasian equilibrium. So this is an if and only if.
It just says that since the VIs can be anything.
VI can be anything.
It just says that this matrix is unimodular. Right. You have no integrality gap.
You have no integrality gap.
For 0, 1.
Wait, what? Totally unimodular is a condition on the constraint matrix where all of them will be.
Yeah, so
Yes.
all of that. So this is,
No, but it's for which valuations is the solution to this magically integral, right?
Yeah, exactly. So
Yes.
this should be for
Totally
every valuation.
unimodular, though, is a condition on the constraint matrix where for every valuation.
That's
It's,
right. But isn't that what you said?
It's okay again.
Every
So
valuation.
for
She wants
no,
it
but
for
here
every
I mean
for a
fixed
particular
evaluation.
Totally
Yeah, fixed evaluation.
definitely.
Yeah.
So here you say for a given valuation, you fix a valuation.
You-
and
you-
only
you-
for this do you want
I-
no integrality.
Yes,
Okay,
yes. And which board is better?
yeah.
Both are equally well. So let me show you, because we have until what time do I have? 12:30. Okay, so I have a lot of time. I can show you. Yeah, there is a whole board. So let's take a look at this. So we have this max.
So the dual is also just kind of a pricing problem.
Yeah, exactly. Let's go to the dual. Let's write the primal and the dual, and then we will derive together this theorem. Okay. So what we have here, we want to maximize the sum of IS of XIS, VIS. Yeah, let's call it XIS now, just to confuse the enemy. Such that for every I, we want the sum of S, XIS to be at most 1, and for every J, we want the sum of I and S such that J is in S of XIS to be at most 1, and we want xis to be greater or equal than 0 for every I and s. Okay, this is, let's call this the primal program. And let's write here the dual program. So in the dual program, what we want to do is we want to minimize the sum over I. Let's call this ui. The variable for this constraint we'll call ui, and the variable for this constraint we'll call pj. And this is, so what's your name? So just like Ankur said, this is not, this is intentional, because this will actually, as we will say, the interpretation of this will be the prices of the items, and the interpretation of this will be the utilities of the agents. Okay? So we want the sum of ui plus j in s pj to be greater or equal than vi of s, and we want ui and pj to be greater and equal to 0 for every I and for every j. Okay, so we have the primal program and we have the dual program. So now the first thing that I would like to show you the first thing that I would like to show you, and this is something that economists always call a first welfare theorem. Although it's just, in the spirit of this, it's not exactly this, is that if a Walrasian equilibrium, let's call it SP, exists, then it maximizes social welfare among all feasible fractional solutions. Okay, so this is very strong. It's not only maximal among all, integral solutions, but among all fractional solutions. And the proof is actually very simple. Because this is a Walrasian equilibrium, we know that for every agent I, this bundle Si maximizes the utility of agent I. So we know that Vi of Si minus sum j in Si pj is greater or equal than Vi of S minus the sum of j in S pj. This is for every I and for every S. This is just the definition that Si is the demand of I under these prices. Okay, now what we can actually do, let's call the optimal, let's X be the optimal fractional solution of this program. So what we know that the sum of X I S for every I is at most 1, because we know it's a feasible solution. So we can just add it here, because this is smaller than 1. Okay? I multiply, yeah. So this is the sum, and I multiply by this formula. But this is smaller than 1, so I can multiply here. And let's see what we get. Now, let's now sum everything. Oops. And now let's do a summation over I over this whole expression of every side, okay? So what we have, let's look first at these expressions. So basically we have, with this, when we sum with I. So what do we have here? Here we have the sum of I, sum j in Si, pj. What is this? If we know that this is a Walrasian equilibrium, this is what we started with. This is just the sum of all prices in the market, right? Because we know that S is a partition, and all unsold items are priced at 0. So this is just the sum of all prices in the market. If we go to this thing here, together multiplied by this, and we sum over all I, because this is at most 1, we know that this is at most the sum of all prices in the market. And in particular, what it means is that sum of I of VISI is greater or equal than sum I of this, where this is exactly the optimal fractional solution.
The signs are minuses. It doesn't go the other way.
No, because we know that this is greater than this, and this whole thing is greater, so this must be that this is greater than this. Okay, so here we just prove that if a Walrasian equilibrium exists, then it maximizes social welfare among all fractional feasible solutions. So this is the if side. And the second, okay, for the second, let's do it just through. So let me show you. So the second theorem says that if we have an integral solution that optimizes social welfare among all fractional solutions, then we know that it can be supported as a Walrasian equilibrium. Okay, so let's say that S is such a solution here, and now let's look at the dual program, and let's call UP be the optimal solution to the dual program. Okay, and what I will claim is that this solution here, S from the primal and P from the dual, is in fact a Walrasian equilibrium. Okay, and how will I do it? I will just do it through complementary slackness conditions, which are sufficient and necessary for the optimality of the primal and the dual, and this will be very simple. So we know that if we have an agent I such that XIS is greater than 0, and in an integral solution what it means is that it equals 1, then we will have that. Now we'll look at the dual program, and we know that UI must be equal here to Vi of S minus sum j in S Pj. Okay, this is complementary slackness, and we know from this constraint too that this must be greater than this thing for any other S, which means that we require the first condition of Walrasian equilibrium. And again, for the second requirement of a Walrasian equilibrium, we'll take this condition, and we will say that if this is smaller than 1, in an integral solution, it means that this is 0, so this is unallocated, this j is unallocated, then we must have Pj equals 0. And this exactly gives us a Walrasian equilibrium. Okay, so this is exactly gives us the whole characterization, which is very, very useful, because what it means that we do not need to worry about prices anymore. We can just characterize a Walrasian equilibrium through the allocation. Okay, we know if it's, and we will see that it's useful in the following slides. So this is for a Walrasian equilibrium for item prices. Now let's take it a step forward to, I defined now bundles. And a straightforward corollary of this is the following. We want an allocation X to be a combinatorial Walrasian equilibrium. And what we have is that this is a combinatorial Walrasian equilibrium if and only if the optimal fractional solution to this LP. What is this LP? I just restricted the allocation even more. Now I don't talk about item J in M anymore. I talk about Xj, which is the bundles that are defined by this allocation. And again, now this is not J in S, but Xj in S. So this is exactly the same linear program, just redefined for the bundles of this allocation. And we say that it's a combinatorial Walrasian equilibrium if and only if the optimal fractional solution to the LP restricted to bundles that are unions of this allocation, just like in this constraint here, occurs at the integral solution that sets it to 1.
It's a little confusing that you call this an allocation, even though it's a partition from which an allocation to the bias will act.
Yes, so I use it interchangeably because it's convenient for me. Because it's, so you are right that in the end it won't be an allocation, but we can also, I can also call it an allocation for what it will be later.
But it's not quite also because this does not yet assign which buyer will get which item.
It's
just a partition of the item.
Yeah, it's true. But I mean, but I say that in the end, I mean, you can see here that actually the integral solution will be exactly to allocate. So in a sense, I can think about it as I want a specific allocation, and I'm trying to think whether it can be supported in a combinatorial Walrasian equilibrium.
Okay.
So then
you
it's
mean that there actually will be no unions. They will each get, yeah.
I mean, I'm also allowed to do unions.
I know, but in the optimal solution, there will be no union.
Yes.
So you are already defining the partition is the solution you will get.
Yeah, I can define it this way. Okay? I mean, you are right. In general, I can allow unions. I can allow unions. This will be just the same in terms of the theorem.
Yeah, but it will not happen. You are just
Yeah.
when an allocation, so the allocation is both a partition.
Yeah, but this is just a definition, right? I mean, in general, I can say that, I allow unions. And in fact, in some of the algorithms that I will show you, I will show how to build those unions in a sense, and then it will define a new allocation, which would be unions of bundles. And I can just, as well call the end product. The end product defines some partition, some allocation, so let's just call it the allocation. But it doesn't mean that the algorithms will not build up unions. They will build up unions. In the end, there will be some allocation, so I call it, al shum sofo. Okay. Okay, so now back to your previous question. You said, why not just take the optimal partition, the partition that gives us the optimal social welfare, and take this. So what I will show you here is that, in fact, not only that this is not true, sometimes we do not have any solution, any combinatorial Walrasian equilibrium X that gives us the optimal social welfare. So let's read the theorem, and then let's discuss it a little bit. So what I will show you here is that there exist valuations such that for every combinatorial Walrasian equilibrium X, the social welfare of X will be at most 2/3 of the optimal social welfare, meaning that a constant loss is unavoidable. Now, for those of you who are familiar with the literature on truthful mechanisms in combinatorial auctions, you know that there is this set of VCG mechanisms that optimize social welfare and can be supported in a truthful mechanism. So in a sense, this tells us that unlike that literature, here sometimes we just have unavoidable loss. I mean, we may have cases where no matter how hard we try, and this is not a computational result, okay? In the literature on VCG algorithms, we say, okay, yeah, we have a mechanism that gives us optimal social welfare. However, to compute it, it's an NP-hard problem. We cannot compute it, so let's relax to approximation and let's see what's going on there. Here, it's not a computational problem at all. This is an existential problem. For every CWE, it gets at most 2/3 of the optimal social welfare, disregarding computational concerns. Okay, let's look at the example. So in this example, we have 3 agents, and we have 3 goods, A, B, C. And these are the valuations of the agents. Every agent here values its own item at 1. This is on the diagonal. And every pair of other items at 2 plus epsilon. The optimal solution here, and this is a XOR valuation, meaning that every agent gets the maximum among what he gets. So if he gets all 3 items, he still gets 2 plus epsilon. Okay, so in this sense, we call it XOR. It's the max of OR. Great. So what is the optimal allocation here? The optimal allocation is just to give every agent its own item for a social welfare of 3. And the question is, can it be supported in a combinatorial Walrasian equilibrium? And the answer is no. Why? Now we can go back to the characterization that we have. We see that we have a fractional solution that gives us better social welfare, right? If we give every pair with probability half, then we get slightly more than 3, which means that this partition cannot be supported in a CWE, which means that we must bundle at least 2 items together, but once we bundle 2 items together, we can get at most 2 plus epsilon in social welfare. 2/3 we don't know. So this is the tightest that we could get. The positive result that we have is that we always have a CWE that gives us at least half. So we still have this gap.
But there you allow atoms to be unsolved, and here you still want not to.
Yeah, but even when we allow items to be unsolved, we don't know how to get anything better than 2/3 here. Okay, so it's true that this. Yeah. Okay. Yeah, so we definitely still have this gap between 2/3 and a half. We try different approaches to close it. We try to go through the integrality gap of the corresponding matching problem with the linear program, but this gives us only half. We couldn't shrink it any further. You are welcome to think about this, and I mean, I'm very interested in this problem. Okay. I believe that. I believe that the truth is 2/3 actually. Yeah, but it's just, it's just a belief. It can be wrong. Okay, great. So here we see that the optimal allocation cannot be supported in a CWE, and so this is just what I said. So we have a loss of 2/3. Okay, and here is the main result of this work, and the main theorem here says that given an allocation y, and now, Jing, you can see this now addresses your question of in what sense this is computational result, okay? So the theorem says that given an allocation y, we can find, and now when I say find, I mean in polynomial time, given what we call demand queries. This addresses what is a oracle model with a demand oracle, meaning that the oracle, what I give an agent a vector of prices, and he responds with the bundle that he likes the most, that maximizes his utility. So given an allocation y, we can find in polynomial time, given an oracle, a CWE XP that gives us at least half of the welfare of y.
This demand queries are also probably in general non-polynomial time.
Right.
It's like answer.
Yes, exactly. But
Players cannot actually implement.
players cannot really implement them, but this is because the valuation is an exponential object, this is usually assumed. So there are 2 models of oracles, value queries and demand queries.
Oh, yeah, but what is really probably a more reasonable model in general, not just in this work, is that players have some program using which
Yes,
given
it's true.
It's a circuit.
Yeah.
It's smaller.
Yes. Yeah, so demand queries, you give the oracle a set of prices, and you get the bundle that maximizes the utility. Yeah.
So players can solve the optimization problem.
Players can solve knapsack. Okay, these are very powerful players.
If there are multiple bundles that all maximize their valuation, they will respond all, or they will
Just one, arbitrary one. A value query is you give it a set, and it responds with the value of the set. Okay, and there are separation results between demand queries are much more powerful than value queries. Every value query can be implemented with a polynomial number of demand queries, but not vice versa. Okay, great. So this is the result. Now, what it means. So first of all, I'm starting here with a given allocation. So obviously, as a corollary, we get that there always exists a combinatorial Walrasian equilibrium that gives us at least a half of the optimal social welfare. But this does not mean that we can always compute it. And we already have lower bounds that prevents us from a stronger result than this, right? I mean, we know that we have some square root m lower bounds. So obviously, we cannot have half of the optimal social welfare in polynomial time. But this means that if somehow, in a miraculous way, I get some allocation y, I can always get at least half. Great. So the corollary is that you can always, this is an existent.
So you showed us that the social welfare cannot always be achieved.
Right.
But how bad will the optimal how good will it be?
I'm not sure I follow your
Again,
question.
Take the optimal allocation.
Optimal allocation, yeah.
Allocation. It has the largest social value, the largest source of social welfare value. Here you're saying that you can use it to find another allocation, which will have
half
the social
Yeah.
welfare.
Well, you can use it to
It will
find.
refine, and it will be a refinement of that allocation.
It will, yes. It will, so all, yeah, so I'll show you the algorithm, and what it will never break bundles apart.
Right.
It will be.
It's not allowed to break bundles apart because it's supposed to be a solution to the Walrasian problem on this.
Yeah, but even during the process, I mean, once let's say it merges two bundles together, even this, it will never break them apart either. It will be a very aggressive, greedy process. Okay, and this half, I don't know if this answers your question because I'm not sure I follow exactly the question, but this half will be tight with respect to our algorithm.
That's our way.
Okay, so let's go to the algorithm, and then if you have more questions. Let me just add a small note about the interpretation of this result. So in the literature of algorithmic mechanism design, we are very interested in this general problem of whether we have a reduction from an algorithmic problem to the economic problem. And usually what we care about is a truthful mechanism. People here are familiar with the notion of truthful mechanism?
Gave us several tutorials.
Okay, great. So you're all experts now. So what is a mechanism? A mechanism gets values as input, and it outputs an allocation. And in order to satisfy some economic properties, such as truthfulness or other things, in my case, what I want is a CWE, I allow the mechanism to also have some payments, to add payments to the players, not just allocation, but also players. And a big question in algorithmic mechanism design is whether, let's say we have some algorithm here that gets values as input, and it gives us some alpha approximation, allocation which approximates the optimal social welfare with some alpha, whether it can be used in a mechanism to get a good allocation. In this sense, whether we have a reduction from the algorithmic problem to the economic problem. And in general, for truthful mechanisms, this is known not to be the case. And in my case, the interpretation of the theorem that I just showed you is that we can take any algorithm that gives us some alpha approximation, feed it to our process here, to our algorithm that I will show you next, and get a mechanism that gives two alpha approximations. So there is not really a gap between the algorithmic problem, at most factor 2, between the algorithmic problem and the economic problem. We assume full information here, yes. Yeah, so this is what I say. I mean, in general, we can think of different goals. If the valuations are private information, then we can think about truthful. The goal will be to design a mechanism which is truthful, in which the agents have incentive to say their truth values. Here, I assume full information, so this is not the challenge. The challenge is that this mechanism, this allocation and payment, will be a CWE. And what I show here is that we have no gap between, up to factor 2, between the algorithmic problem and the econ.
So the goal is to say, give you an allocation,
Yeah.
you have mechanism to allocation plus payment.
Exactly. That gives us the same approximation up to a factor 2. Okay.
Maybe one way to, even though you didn't show the algorithm, one way to ask my question is the following.
Okay.
So it seems that the integrality gap of this program, this primal program, is somehow key to. So, for example, if there is no integrality gap, you know that.
Yes.
Okay. Now, suppose you get an optimal allocation for this, so social allocation which maximizes social
Yes.
welfare, and you update your program so that you are allowed to take on unions of this.
Mm-hmm.
Right.
Mm-hmm.
What is the integrality gap there? So
So I don't know. The answer is that I don't know.
It's possible that it's just 2, for example.
It's
right?
possible,
Yeah.
but I couldn't prove it.
1.5. Yeah, so you
Yeah.
try because you get a lot of information. You know that's
Yes.
this is the optimal
Mm-hmm.
allocation.
Mm-hmm.
The program simplifies it.
It's true, but I
I don't know.
I
And
don't
it
know.
doesn't follow from what you prove?
No.
Well,
That-
maybe
so-
it does,
So let me show. Look, because what I prove, I get it tight only with respect to the specific algorithm. But I do, you don't. Let me show you. Let me show you the algorithm.
Just before, you're getting, refinement of the given allocation.
Yes.
In particular, if it was optimal, you get refinement of the optimal.
Yes.
It will be, what you define to be a combinatorial Walrasian equilibrium, which if you start already with that partition from the optimal allocation,
Mm-hmm.
it is a Walrasian equilibrium for this restricted problem. Right, it is.
Only if it doesn't have. Only if in the end it doesn't have an integrality gap with respect to the new bundles. It will be a combinatorial Walrasian equilibrium.
So for example, take her old example, right, with the ones along the diagonal. So there the optimal partition is vacuous, right?
The optimal partition.
I mean, the optimal, allocation is just singletons.
Oh, it's singleton. And then
So
you
it
get-
gives you
okay,
no
very good.
restriction.
Yeah, yeah.
So I mean, I don't think, I agree with you. It's the,
But
integrality
here
gap
it's
that
the
is-
integrality gap is 3 halves. So maybe I'm right still, right?
Yeah, no, I agree, but it's, like, I don't know, that's,
Maybe this is the. Yeah, I couldn't prove it.
So it's possible that maybe that just that integrality gap is a solution to the approximation problem. I mean, certainly one solution you could just, I mean, if you had a good rounding technique, you could just solve it, round, and I don't know how that, and that may be a different way to get the integrality gap.
Yeah, maybe. Okay, good. So now we are ready to go to the. Okay, so yeah, so like the interpretation like the way I would like to think about this result here is that there is no clash between the algorithmic and the economic concerns. Okay, unlike in the literature on truthful mechanisms where there is a clash. Once you go to approximation, all the incentives are getting messed up. Okay, so now we are ready to go to the construction. So what is the goal? The goal is to take a given allocation y and to convert it into a CWE XP. And the idea would be, just like everybody here guessed, to set the initial bundles to be just like the allocation that we got, and also to set some high prices, and I'll say what I mean by high, and then attempt some, this atonement process where prices increase, and then we'll terminate with some allocation. Okay, so let me say a few things about this process. So first of all, it will be a very simple and natural process. It will be a monotone process. Indeed, price will only increase. In addition to the increase of prices, there will also be some merging of given bundles. And it will be a very aggressive process in the sense that once an agent comes to the market and wants a bundle, given the current prices, I irrevocably merge them together, never break them apart, okay? And because this is going to be a very aggressive process, I must start, in order not to lose too much in social welfare, I must start with high prices. Otherwise, if I start with 0 prices, just like the original atonement process, an agent comes, wants everything, obviously I lose all my social welfare. Okay, so I have to do it in a clever way that on the one hand gives me high social welfare and etc. So here is the process. Initially, these are the buyers. They all start with 0 endowment. They don't get anything. And this is the original allocation with some prices, which I'll tell you later what are the prices initially. Then I do a greedy process, and every time I take an arbitrary agent that does not get his most demanded set, let's say this agent here, and if the demand set DI of this agent is uncontested, meaning that it is not currently allocated to anybody else, I just allocate it to this agent. If he wants a bundle, I would bundle it together and allocate to this agent. So, okay, so this agent got this yi at a price of P2. Now this agent, he wants the bundle y4 and y5. I bundle it together. I update the price to be the sum of the original prices. And that's it. Now another agent, he wants y1. I give it to him at price P1. Now comes a new agent, and this agent actually wants y2 and y3. Okay? y2 is contested because y2 is already allocated to this agent here. So what I will do, I will just, because he wants something that is greater than one item, I will just bundle it together, update the price to be the sum of P2 and P2, and allocate to this guy, and this guy is now not allocated anything. Okay? The only time in which prices will actually increase is the following. Let's say this agent here wants a single item that is currently allocated to someone else. Now it's a competition between them, and I will gradually increase the price of P1 until it will reach some price P1 prime where one of them will drop, and then this agent here will get it for a price P1 prime.
So you will not do it after a bundle was created?
No. Because when a bundle is created, it's enough to progress the process. It's fine for me because things get smaller and I'm fine. Okay? So this is the whole process. And I will just continue this until the process terminates. And then I claim it will be a CWE, and it will give at least half of the social welfare. This is what I'll show next. Yes?
But this single player can also want this bundle y2 and y3 together, but he has a competition with the last player.
Yes. So here, for example,
Yes.
so
At this point, this star
at,
player,
oops, at this point,
one step before.
yes.
One step before. I mean, yes, this star player
Yes.
may also want the bundle y2 and y3.
So now it's a single item. Now y2 and y3 is no longer a bundle, it's one item at a price of P2 plus P3.
That's what I asked before. So then price will increase there also?
Yes, yes, yes. Because once, that's what I say, once you bundle something together, now it's an item. It's not two, okay? So then this is one item at a price of P2, P3, and if this agent now wants this, prices, the P2 plus P3 will increase until one of them drops. Okay, so this is the whole process, okay? Very simple. Agents come, claim their demanded set. If there is a competition over one single item, the price will increase until one of them drops, and that's it.
How to set up the initial price?
Great question, and I'll show you this in a minute, okay? So, right, so this is just describes the process. And so now let me show you. So let me show you now first why it's a CWE, and second why it gives me a half social welfare, and I mean what prices should I initially set in order to get it. So first of all, the algorithm terminates because prices can only increase and bundles are never split, so we know that it terminates. By the way, in this version, in the paper, we actually show how to do this process in polynomial time. Here I didn't show you how to do it in polynomial time because it's too complicated. I don't think it's worth the time. But if we are careful, we can also make it terminate in polynomial time. Okay, we'll just need to add a few things to hurry up the increase of prices, not to do it very gradually, but after each iteration of the process, we'll somehow get the prices high to be maximal with respect to the demanded allocation, and things will be fine. And obviously, upon termination, I mean, by the definition of the process, I mean, every agent comes and gets its most demanded set, so obviously, in the end, the allocation will be CWE, right? So now I just need to show you that it gives you half of the optimal social welfare, of the original allocation. So the question is, how should we set initial prices? So we know that the original bundles are Y1 to Yn. And what I would do is I would price initially every Yi to be half of the value of this Yi in the original allocation.
So it's really important that the number of parts is the number of players.
That the number.
Parts, the number of the exactly n bundles. If you start with an allocation really, not just a partition. Partition to n parts.
Yes.
And if you start with n parts plus some remainders.
So this is fine because.
Not complete allocation.
No, but I can, if I start, no, it's important that I start with an allocation. It's true.
Even though at the end you don't demand the market.
Right,
clear,
right.
you want to start with something
Yes.
that does clear the market.
Yes, and in an optimal, I mean, the optimal allocation, I can assume without loss of generality that it's n allocation. Right. Right, and this is what I'm going to show you next, the two approximation. Okay, so here is the proof. So this is the original allocation, and as Evie said, this is exactly matching. We have n agents, and we have this y allocation, and we remember that under this matching, we have value vj of yj for every bundle. And here is the end, the allocation in the end of our process. In the end of our process, we have some unallocated items. As I said, I allow this. We have some allocated items. These are actually maybe, I mean, this xk may be a bundle of different yi's because I may, bundle things along the process. And we have some buyers who are allocated some items and some agents that are not allocated anything. So this will be the end process. There should be? Yes. Right. Yeah. Yeah. This is true. Okay, so here is two very simple observations. Observation one, if yj, if we have some bundle here that is ever allocated, it remains allocated throughout, right? Why? I mean, if you remember the process, the only way it can get unallocated is if it's allocated by another agent. What this means is that if we have an unallocated bundle here, it means that it's an original yj, because it was never allocated, so it was just one of these yj, of these blue rectangles. So, and we originally we priced it at half vjyj, so its price is still half vjyj. Nothing happened to this bundle along the process. Observation two, every yj, every such rectangle that is unallocated, in y, it must be matched to one of the allocated buyers, to one of the buyers that in the end of this process get allocated something. Why? Because if in y it was allocated to one of these, it's priced at half vjyj. They must want it. It can't be that they don't want it, so it can't be that the process terminated. Jing, something bothers you?
The unallocated bundles must be most wanted. The j is the j that gets something at the end.
Because your j most wants bundle yj.
Let's say this agent, let's say this unallocated item in y, it was given to this guy. Yeah. This guy values it at vjyj. And the price of it is half vjyj, so how come it doesn't want it now? But he doesn't get anything.
Sure.
So he is now in the pool of unallocated buyers. He comes to the algorithm, and the algorithm tells him, under these prices, what do you want? And he says, I want nothing. How can it be? I mean, if he gets this, he gets positive utility.
Right. Okay, he must want something. He may not want exactly this one.
Right. Yes. So the fact that he is unallocated at all means that he can't be matched to this thing under y.
But that's not clear how you implement this in the... You use demand queries. So like Jin says, this guy will not ask for y. It will not
He may ask for something else.
Yeah, so
yes.
You wouldn't know that it's...
No, but he may ask for something else.
The algorithm know? Yeah, he may ask for something else which he cannot get.
Mm-hmm.
How does the algorithm know?
Price will increase. It's one item, the price will increase in the end he won't want.
In the end, even if he wants something else, he must be allocated something.
Because
we don't know that he wants yj, but we know that if he didn't get anything, he must prefer yj to his current situation.
He wanted something
Yeah,
else,
no,
the
but
price
that's
of
what
something
I-
else would increase. So at some point you want it, you fall back to this to his original.
Okay, so we know that originally in Y, all the unallocated bundles are given to agents that are currently allocated. So now we have a way to charge these valuations from the welfare of Y using these two observations. So first of all, what is the social welfare? The social welfare is just the sum of the valuation of VIXI. We can actually write it as the sum of the prices of I and the utilities of I, right? Because the utility is just the difference between VI and PI. So now let's see what we will do. We will look at the YJs that are allocated, and we know that all the YJs that are allocated are parts of these X's that are currently allocated. Originally, they were priced at half VJ YJs. Prices only increased. So we know that the sum of the prices of I that are being allocated is at least this sum here. Now, what about the YJs that are unallocated? How would we charge them toward the social welfare? Just because of this observation, we know that these are at Y are matched to agents here. And we know that these agents here currently are happier than if they would get these. If they get these, they get half the VJYJ. So now they must be happier. So their utility must be at least this half VJYJ, and then we just get exactly half of the social welfare of Y. So this completes the proof of these two approximations. Okay. So now that we know, so let's now. Yes.
So you know what you have an algorithm, it found some allocation.
Yes.
You know how it compares with the fractional solution of the way it relates to the question I asked before. I'm just wondering how.
So to the fractional allocation given these bundles, it must be optimal because it's a CWE.
So that means that the integrality gap under this partition of your program is
Yeah, but this is already with the new bundles.
Yeah.
Yes.
That's what I asked.
Yeah, but it doesn't mean anything about the original problem.
No, it doesn't mean. I'm just saying that if you partition things according to the optimal allocation in the linear program, what
Yes.
you actually prove is that the new program has integrality gap to the factor of 2. No?
If you refer to the new program as the program where the bundles are defined to be the end process, like the end product of this process, then yes.
The beginning.
No, the beginning I don't know. Because I don't know anything about the original. All I know is that in the end it will be a CWE. I don't know that in the beginning it was a CWE. So now some additional questions. So to Klim's question, can we achieve the same result in a CWE with market clearance? So remember, I mean, in this process, we had some unallocated items that are priced at price greater than 0. Can we achieve it with market clearance, selling everything? And we don't, yeah?
Why can't you just now, after you have this equilibrium, you can start to reduce prices? Why not?
It will ruin the incentives. It can completely change the demands of the agents. So I don't know how to do it and preserve the original demand set. And once the demand set changes, I don't know what will happen. I mean, there might be a way to do it, but I mean, I thought about it a lot, and I couldn't come up with a way to. Yeah, so the natural thing to do would be, okay, so we got this, now try to play with prices, reduce them in a way that will somehow preserve something, but I don't know how to do it. Okay, so in general, the problem is still open. We don't know. We don't have general result. What we do have, we have some results for specific valuation functions. Okay? For example, for superadditive valuations, we know that you can always support actually the optimal allocation in a CWE. You get no loss, not even this factor 2. Okay, superadditive, sorry. Superadditive is some notion of complementarity, and what it means is that VI for ST that are disjoint, VI of S plus VI of T is smaller or equal than VI of S union T. You want the bundle more than the sum of the original. This is a superadditive. And a subadditive is the opposite. Okay, and we know that gross substitutes is contained in submodular, which is contained in subadditive. Okay, so I'll show you some valuation function for which we can say something about market clearance. In general, this is still open. The second question is, so all along this talk, I assumed that the valuations are common knowledge, and the question is, can we design some mechanism that will result in a CWE, but also be truthful in the sense that agents will have incentive to tell me upfront their true valuations. Okay, so we have some questions here. I don't think I will get to them. Okay, so let's go to the question of CWE with market clearance. So as I said, for various classes of valuations from both sides of the map, both from substitutes and complements, we know that we can obtain nearly optimal social welfare in a CWE. I'll describe to you two classes, one from complement side of the map and the other from substitute side of the map. Superadditive is what I defined here. For this, we know that there always exists a CWE that incurs absolutely no loss in social welfare. Obviously, this is an existential result, not an algorithmic result, because we have lower bounds, very strong lower bounds, computationally wise. And we will also talk about another valuation class, which we call uniform budget additive. I'll define it. This lies in between gross substitutes and submodular. So it is more general than gross substitutes, but it's still pretty restrictive. Great. Okay, so superadditive valuations. So it means that Vs plus Vt is at most V of S union T. And what I show is that if valuations are superadditive, the optimal allocation X with, if I price it just at the valuations, it will give us a CWE. And the way to see it is actually very simple. So we know because we know that X is efficient, we know that the value Vi of Xi plus the sum of J, Vj, Xj, we know that X is optimal, so it's better than to give I both Xi and all the Xj's. So we have this inequality. And from superadditivity, we know that this is greater than Vixi plus Vi of the union of J, Xj. So this gives us that the sum of J, Vj, Xj is greater than Vi of the union of this Xj. And now I can use it to get the following. So what I need to show you is that Vixi minus Pi, which is the utility of I need to show to you that this is the most preferred thing for agent I. We know that this is equal 0 by the definition of Pi. Pi is just set to be the value Vixi. From inequality 1, we know that 0 is greater than this thing here, which is the difference between Vi of the union of Xj's and sum of J, Vj, Xj. And again, if I just use the payment, the definition of the payment, I know that this is exactly the payment of the J, so I get exactly what I wanted. Okay, so I know the I is maximally happy. So for superadditive, things are very simple and very nice. I just get optimal social welfare. Now I go to the more interesting case, and this is what I call budget additive valuations. And let me first define it, and then we can get a feeling of what it is. So what are budget additive valuations? Every agent has two objects. One is some budget, which we should, it's not really a budget. We should think about it as a cap to how much he values any bundle. And this is given by BI. And he also has some value for every specific item. Okay, VI1 to VIM. This one every agent has. And the valuation of every agent is additive up to this cap, up to this budget. In other words, for every bundle S, the value of agent I to this bundle would be at most BI, because I said this is the cap. But if this cap is not binding, I just get the sum of the item valuations. Okay, this is clear? I mean, that's just the definition of what this class is. Great, okay. And as I said, this is more general than gross substitutes. And even this next restriction that I put on it, it's still more general than gross substitute. What's the additional restriction? I also assume that valuations are uniform. What does it mean that valuations are uniform? It means that every item has some value, and if that agent value this item, this is the one value that we have. So for every column in this valuation matrix, we have some empty boxes which are just 0, but if there is a value, then there is one value for every item, which is the same across agents. So every budget additive valuation is given by such a matrix where every agent has some budget and some valuation where the columns are identical. Okay, so what do we know to say about this class? So we know that if valuations are uniform budget additive, that strange valuation function which I just described to you, then there always exists a CWE with market clearance, such that we get at least half of the optimal social welfare. And in fact, if budgets are identical, then we get even a stronger result. We get no loss at all in social welfare. We can always have a CWE that gives us the optimal social welfare. And I won't go in detail over the analysis, but the analysis will be based on, again, the configuration LP for this problem. Okay, so two things to note here are the following. First of all, a uniform budget additive, even with identical budgets, okay, for which we get this strong result, that we get no loss in social welfare, even, so you may think that if I restrict my valuation function so much, maybe it even has a Walrasian equilibrium. So of course I get no loss in social welfare. And the answer is no. We have instances in which, let me do it here, in which we get no social welfare, in which we get no Walrasian equilibrium. And here is such an example. So let's say, this will be an item, and this will be an agent. This will be the budget of the agent, and this will be the value of the item inside the box. I will write them, and I'll describe in a minute. What I do here, okay? So this will be budget. All the agents, these are the agents, they have budget 2. All the agents have budget 2. All the items have value 1, except for this item here, which has value 2. And what this graph describes is what agents want what items. Okay, so for example, this agent has budget 2, and he's interested in these 3 objects. So this is definitely an instance of uniform budget additive valuation. And let's see, let me show you that this instance does not have any Walrasian equilibrium. Again, what is the way to show that it doesn't have a Walrasian equilibrium? You already know that. I will show you that there is an integrality gap. So what is so it's pretty easy to see that the optimal integral solution here is 7. So for example, this agent can get these 2 items, and you know, you can give this one that item, and this one these 2 items, and yeah, 7. Okay, I mean, maybe I didn't do it right, but you cannot, I mean, the one thing to notice here is that you cannot get up to 8. You cannot get a social welfare 8 because you have no way to satisfy. Of course, you can't get more than 8 because the sum of the budgets of the agents here is 8, so you cannot get more than 8. But in an integral solution, you cannot get all the 8. You can only get up to 7. Whereas in a fractional solution, you can get all the 8 because you can do, for example, to this agent, you can, with probability half, give these 2, with probability half, give these 2, and then for this agent, with probability half this, and with probability half this, and then exactly the same symmetric thing in the other half. So even this very restricted valuation class, which is a uniform budget additive, it's beyond gross substitutes, and moreover, it does not have a Walrasian equilibrium. Nevertheless, we can have an optimal CWE with optimal social welfare. Yes?
Why economically do you care about market clearance at all? I mean, I see it's follows from maximum social welfare. But why
So the economic motivation for market clearance is that if there are items that are priced above 0, it's not an equilibrium in the sense that the seller would want to reduce the prices, because why would he want to, you know, stay with a banana that he will just reduce the price until it's sold, and then he can gain more revenue. So in that sense, it's not an equilibrium from the seller side. Okay? But it's a great question. Okay. Okay, good. So this is the first remark. So even though it's very restrictive, there are still cases where it doesn't even have a Walrasian equilibrium, so it's still interesting. And also another remark is that there exist uniform budget additive valuations now with general budgets where you get a loss for every CWEX. Okay, so this result here is specific to the case where the budgets are identical. Let me tell you, in terms of the computational aspect of the problem, even if budgets are identical, the problem of social welfare maximization is APX hard. And I believe that the best... Yes. And the best known approximation is 4/3. So what it means is, if we go back to that figure that I showed you, the reduction from algorithmic to economic, it means, for example, that for this class, we can take the 4/3 approximation, just the algorithm, and we can turn it into an 1/8 approximation that gives us CWE in polynomial time. Okay, I think you look tired. So maybe I won't go over the rest. Let's jump to conclusions. Never jump to conclusions. Great. So what I showed you today is I introduced this notion of CWE. I believe it's a natural relaxation of Walrasian equilibrium, which always exists. And the main result is that not only does it always exist, there always exists such a solution that gives at least half of the optimal social welfare. We also saw that a constant loss is unavoidable. So in some sense, this half is the most we can hope for. I mean, except for this gap between half and 2/3 that we have. And another important thing that I convinced you, I hope, is that bundling is essential. Because if you remember the first examples where we were hoping that by just relaxing the seller's side equilibrium, maybe we can support good social welfare with just item pricing. I showed you a linear gap if we do item pricing. And the main open problem is whether the same result holds for CWE with market clearance. We don't have these two approximations. We have only once we relaxed market clearance with bundling. We don't know if we can still get it without market clearance. We know that it's true, for example, for super additive and for uniform budget additive valuations, but we don't know it in general.
In general, if you just reduce the prices, this algorithm can show that it will not work?
Yes, yes. Because like the structure of the demand can change drastically. And then you have no way to argue about it and to analyze it.
But you have counterexamples.
Ah, you mean specific counterexample in which you reduce the price?
And then you get much less social welfare than...
I'm sure I can construct an example where, moreover, not that if I reduce the price, I get no CWE anymore. Okay, because then the process might not even converge. You reduce the price, the demand changes, and then it may create cycles, and maybe I won't even have a CWE. Okay, here are some additional open questions. If some of you are interested to work on them. So first of all, what I showed you is that if I give you an initial allocation, I give you two approximations to this allocation, and the question is, what can we do if we don't get anything from scratch? I mean, if we start from scratch. Another question is, what approximation to social welfare can be achieved with item prices for submodular valuations? I believe this is a very interesting problem. If you remember, I showed you for sub-additive, I showed you a linear gap. For gross substitute, we know that there is no gap at all because we know a Walrasian equilibrium exists. And the question is, what happens here for submodular? You ask about this specific question or more generally? More generally.
You look at the CWE, which is a slight generalization
Yes.
of the linear price.
Right. If you are more, open to, to allow, for example, arbitrary bundle prices, then you can obviously get much better results. But then the pricing structure loses its simplicity.
But there is simple pricing structures in supermarkets when you get 1+1, all this kind of, when you are allowed, so supermarkets are still working the way there is these structures when you allowed to take, to bundle two items and say that their price is less than some of each prices of each item.
Yes. Yeah, I mean, I think it's a very, very interesting problem to think about other price structures that are in between this CWE, which is still very close to item prices, and doesn't go all the way to arbitrary bundle prices. I think this is a very, very interesting problem. Yeah, what can you still get such good results and still be simple? Okay, like in a sense, how simple can you still be and get good approximation to social welfare? Okay, so, because like, obviously, a very important economic goal is to keep the prices simple. Okay, it's simple. It's also fair in a specific sense. So you want to keep it simple. And the question is, can you keep it simple and still get good result economically? Social welfare, revenue, all this. Okay, another question is, what is a maximal class of valuations that admit an optimal CWE? We don't know anything beyond, we know gross substitute, of course, because we have Walrasian equilibrium, but we don't know above. We know that for uniform budget additive, we know that we already get negative result here. And finally, what approximation to social welfare can be obtained in a CWE and truthful mechanism? Okay, if we require also truthfulness, how well can we approximate? Because all of the things that I showed you today were under the assumption of full information. And that's it. Yes.
I was still thinking about what Ada said a while ago about the units of the bundles. And so in principle, we can have the units of bundles at the final allocation. But as you said, if the original allocation is the optimal allocation,
Yes.
then actually the ultimate optimal bundling is just this allocation itself. Right?
You mean if the original bundling is the optimal allocation, yes.
Then the final, I mean, the optimal allocation with respect to this bundling
Is
just itself.
Yeah, but it may not be CWE.
It may not be CW.
It may not be optimal among all fractional solutions restricted to these bundles.
Oh, so that you cannot just consider single, given this optimal bundling, and consider each pair as unit demand for the separate bundles, and solve this problem and find the CW pair.
No, you cannot.
I see. So for CW, you really may have to consider a unit of the bundle.
Definitely, yes. Yes, it was just convenient for me to define it with the final allocation, but
So it's really, you really cannot reduce it to a unit demand option pair.
no. I mean, obviously not unit demand because valuations can be.
No, I mean, once give you the optimal bundling.
Yeah, even given the bundling, you cannot restrict it to unit demand because unit demand. I mean, what's your value for a union of two bundles?
You can just define a value to be the value for each single bundle, and this will be a new valuation function.
Yeah, no. So you cannot.
You cannot.
Right.
There's something, some kind of cycle going on. You know, you come to the market. I mean, the buyers come to the market. They want to get out. I mean, you want them to get as much social. You want social welfare to be maximized.
Mm-hmm.
In your situation, as opposed to the original one,
Mm-hmm.
some allocation is known. Let's say the optimal allocation. They can just get it and walk on. That
Yeah.
will maximize the
So there is.
value.
Yeah.
Now, they can't do this because
They're jealous. They're
they
angry.
are angry. However, the seller knows it.
Mm-hmm.
Because the seller, it's essential for the seller to know it in order to run your algorithm.
Yes.
And compute prices which will end up in giving the world only half the social value.
Yes.
So, I mean, is there a point in, I mean, if this is
Because there is always, I mean, in economics, we have a clash between the individual incentives and the preferences and social as a whole. This is exactly the clash, right? I mean, we want to optimize social welfare. This is a social goal. But this social goal is composed of individuals with their own incentives, which might clash. And in order to prevent these clashes, you might need to reduce the overall social welfare.
Okay, so yeah, I guess that's the answer. You want them to be satisfied from their own utility
Yes.
viewpoint, and that you can do it.
Yes. And the good news is that you don't need to to reduce social welfare by much, only factor 2, and you get everybody happy.
Okay.
Yes.
So I was just thinking about this, your use of the demand oracle, and wondering about relaxing that. And I was curious what if you just, instead of assuming a demand oracle, assume that people have some sort of personal imperfect demand oracle, where I say, here's a set of prices, try to come up with a bundle that you'd like, and it may or may not be the best for them, subjectively. And then with respect to that, more bounded optimization notion, find some notion of, say that, this allocation is, provisionally CWE if none of the agents can find a better bundle for themselves with respect to these prices. And I'm wondering
can find, you mean in the computational
in
sense?
their personal brains can,
Yeah.
can come up with.
Bounded rationalities,
Yeah.
kind of, yeah.
So I'm wondering if you had, access to these imperfect demand outflows for the agents that, you can say, here's some prices, I want to elicit from you some guess as to your best, choice here. Could we use those imperfect demand outflows to build one of these provisionally CWE, solutions?
I think it's a beautiful question.
So it can be the issue is a circuit that computes some.
Yes, some compute.
For every set of price, compute some circuit.
It could, or it could even be defined more like you could try to run this algorithm you define just with respect to some kind of non-deterministic notion of agents who either succeed or fail, at every stage, and coming up with some demand set or some imperfect demand set
Yeah.
to drive the next stage of the algorithm.
Right.
They don't even have to be consistent with described by some circuit.
So in a sense, you mean to take.
They are consistent as well. Well, because you eventually want to say they couldn't find a better, so who couldn't find a better?
These particular agents, that is like, if you're running some
So
kind of
what
algorithm.
are they? I mean, to say they couldn't do something, you have to somehow say what their limits are.
No, I just want to say that we have some algorithm which at each stage has some kind of provisional allocation, and it elicits from the agents, it says like, is any of you unhappy, right? And maybe none of them have successfully truly optimized with respect to these prices, but they either succeed or failing in coming up with some grumble, some saying like, I would rather have this. And every time somebody succeeds in coming up with a grumble, you can use that to drive progress.
So I think in a way what you are suggesting is that to actually use the fact that agents are computationally limited to get better solution.
Yeah, well, you're relaxing the notion of what a CWE is, but it's relative to, it's somehow justifiable that if the agent can't come up with
Right.
what's right, then there's no reason for them to feel
Right.
There are, there are other notions of computer. I think, now that I understand the good question, I think it's great.
Yeah.
There are, in general, using computational limitations to find.
Yeah, for example, manipulation in. So we have you.
Another dilemma is this old words of Neyman and Wittgenstein and
Of bounded
Fixer,
rationality.
Yeah.
Yes, and there is also more recent work on, you have all these impossibility results that say, for social choice theory, that every social choice function has you have some way to manipulate it. So there is a recent result that shows, well, but finding the way to manipulate it is NP hard, so maybe we can use this to argue that this is stable. Things like that. So in a way, we are used to think about computational hardness as a negative thing, and these kind of results show that we can actually use it to our own advantage.
Ignorance is bliss.
Ignorance is bliss. Yeah.
So I have one more high-level question. So
Okay.
I don't know, this Israelis here may have seen in Haaretz an article last week by
Ariel Rubinstein.
who's a famous economist, and it says, I don't know if it appeared in English also, but he's saying, look, I'm a game theorist, I've been doing this for 30-some years, 40 years, I don't know.
And it's useless.
Game theory is useless for the practical world. If you have economic problems, you shouldn't employ game theorists. So you read it?
Yeah.
Yeah, what do you think?
So first of all, I think it depends how you define game theory. For example, auction theory, is it game theory?
Yeah.
If it is, then auctions are now everywhere, and the theory is being used to derive whatever economic goals, so revenue, social welfare.
I wrote this, he sent me the paper, I sent him, I can think of many examples where
Yeah.
I did, for example, auction theory. So he said that's not quite game theory. I don't know why he said this.
Yeah, so that's what I'm saying. I think it's a matter of how you define. It's just a matter of definition. If you define game theory, yeah, if you define it as the useless part of game theory, which may be an empty set. No, it's probably not an empty set.
I guess you need to take into account the context game theory do options, but that they cannot be. It is useless for public policy
That's
solutions.
quite the way I read it. Well, I don't know if you know him.
I read his book about it.
Yeah, no, but yeah. So, but he likes controversy first of all, so that's very important. But it looks like it's about public policy because the title is about the Iranian bomb and
Yeah.
whatever else, another crucial public policy issue. But at the end of the article, it says, I gave it this title just to attract you to read it. There's nothing to do with it.
And there is nothing to game theory. Yeah.
Okay.
Because it's, because I'm being videoed, I don't want to say any controversial things here.
Okay, thanks.